Everybody's here before the time, so it means that everybody's curious to know how to fold in the information on redshift into gravitational wave detection. Raul,
okay. All right. So this is an idea that actually started in these rooms here about a year and a half ago, I think, right? Something like this. So this is work done with my two PhD students, João Ferretti and Tashiro, also with Isabela Matos, who is a postdoc and looking for a job. Miguel Quartin, who is this guy here, is that guy there. But first, a few words about the. Okay. Okay. Now, this workshop here is a bit about how to combine different probes and how to look at the universe in different ways. So this is just a compendium of some very randomly chosen probes of the universe and how deep you can go. Of course, it doesn't say anything about how many objects you get. You get some of them which are very rare, some of them which are quite rare, and some of them which are quite common. But the idea is that we can probe the universe in multiple ways, not only with the electromagnetic signals, but increasingly also with gravitational waves. I think this is the most exciting thing that has happened in the last many years in cosmology. That's my personal opinion, and it's our challenge how to combine this to make a unified picture of cosmic evolution. I think this is the most interesting challenge here. But first, let me just talk a little bit about about some other survey here, which I think is very interesting that plays into this. So this is JPAS, a survey that I've been involved for the past 15 years, pretty much. And the idea is that we do an optical survey in a lot of narrow bands from this telescope here in Spain. And we have 56 filters with about 100 angstroms. This is going to be up to about 22.5 in the narrowband filters, which is, at least 3 magnitudes deeper than SphereX, for instance. So much deeper survey. We already have something like 300 square degrees already observing all filters, many thousands of square degrees if you count the filters individually, and you can get more information here. But basically, this is what we get. So what you see here in gray are actual spectra, and what you see in the colored dots here are what JPAS sees. So it's like a low resolution spectrum. And there are many things you can do with that. So for instance, we will have about 20,000 galaxies per square degree with photo Z's better than about 0.7%. But on top of the photo Z's, and that's very important, we get also the galaxy properties. And this is really interesting because you can divide galaxies in different types and populations, and that's super interesting for multi-tracer cosmology. We'll also see a lot of quasars. Actually, JPAS will be a superb object survey to detect quasars. These are 2 quasars at different redshifts here. This one is at redshift 1.7. This one is at redshift 4.3. And you can see that you can get the very broad emission lines from quasars. Sorry, there's already questions.
Yes, well, you mentioned SphereX. What's the wavelength complementary overlap?
SphereX goes much more into the infrared, which is the strong suit of SphereX, not so much the optical, but it's much shallower. So, you can get some interesting stuff from the narrow bands, especially on the infrared.
I mean, presumably where there's overlap between the two, you can help use that to calibrate SphereX photo Z's.
I guess we haven't really looked into SphereX in that sense, but it's a possibility for sure. So anyway,
there was one more question.
Oh yeah, right. Sorry.
So what is the comparison in the density with other than quasar? Like this, SST.
So I'll show a direct comparison of DESI, which I have a nice figure of where the overlap, and you can see with your own eyes the difference between the density of object in JPAS and DESI. But for quasars, they're not too different. We expect to have about 30% denser sampling compared to DESI. That's what we expect, and we are now just basically chugging the numbers for this.
So the tens of thousands refers to redshift up to 1-ish.
Up to redshift of about 0.91. And at 1, the redshift performance, the photo Z performance drops a bit more because the signal to noise starts to get a bit low. And we are going to reobserve. JPAS is going to feed into the WEAVE survey, the quasars that we find at redshift greater than 2.2 for Lyman-Alpha forest studies. We already have a lot of data here, lots of papers, and you can see more on the jpas.org. I think this is interesting here. This is DESI in an overlap area. here is DESI with one pass. So the red ones are DESI and the blue dots are JPass. And here is when DESI has 3 times. So when it comes back to the same place 3 times, right? DESI goes to redshift of about 1.6 with emission line galaxies. JPass is limited to redshift smaller than 1. Typically, we see number densities of between 5 and 10 times bigger with JPass compared to DESI in galaxies.
Yeah,
So I think it's interesting to, yeah.
seems that you don't see the same galaxies.
Sometimes we don't see them because they are at a high redshift. Often we see them, but it's overlapping. This just gives you an idea about the sampling that we get there. However, there's an important difference here is that we don't pre-select anything. We don't say we have to see galaxies of this type or that type or that type. We just see everything. And for each one of those galaxies that you see here, we get some measure of the stellar mass, star formation rate, and of course, color, things that allow you to break galaxies into different populations. So I think this is really the greatest advantage of JPass is that you see everything and you get some not very high resolution properties, but some decent enough properties that allow you to break the galaxies into different types. Okay, yeah.
Show
Here?
of the sky coverage, how much are you gonna?
Yeah, so this figure I shouldn't really show. I just I'm glad that nobody asked, nobody took a picture. Yeah, but we have a few seeds in the sky that we are observing. It's quite complicated because the this is our focal plane here, and we have 14 CCDs. Each one of them has one filter, and we have to kind of step and stare to cover a whole area. It's quite complicated how you complete the filter coverage. So we have a few seeds that we are completing with time. So it grows slowly and then goes fast because of the way in which when you join areas, then the whole region inside that area is imaged in all filters, and then you have all the filter information. But if you have just a few patches, then it grows slowly. So in the first few years, it's a bit slower, but then it picks up.
Is what has been done already?
It's
Gonna spread.
Yeah, so right now of all the data, maybe 20% has information on all the filters, because a lot of it is in the border areas where we have only partial filter coverage, right? But with time, when we join areas, then the ratio of surface to volume gets much better. So that's how this works, right? So this is our VO virtual observatory tool here. You can go there and you can just get a region of the sky. You can just say, okay, let me look here. Let's see the objects for which I have data. Then I can, for instance, just put my mouse in there, click in there. I can get the information from that object there. This case is, what is this? I have no idea. It's just a galaxy at a redshift of, where's the redshift? Somewhere else. It's not here, photo Z. But you can get the spectra here. So for instance, you have this pseudo spectrum there. So this is for every object that I showed you before. So you can imagine that this allows you to do some, not only photo Z's, but also to determine which type of galaxy that is. Anyway, why we want that? Well, if we think about galaxies as a single thing, we are missing the point, because galaxies, they can be very different. So this is work that I've done with Natalia and Nathalie and Antonio. Natalia was my PhD student. Nathalie just graduated a few months ago. And this is what you get by separating galaxies into stellar mass and color, for instance. There's a factor of 2 to 3 in bias of these populations here. And this is what you get if you can get a larger sampling of galaxies and you can get their properties. So this is an important point that sometimes gets missed when we talk about multiple tracers, that in order to get really the advantages of multi-tracer, you really need large numbers. So otherwise, you end up being dominated by shot noise in each individual population. So we need large numbers, which JPass has, and you need to be able to separate that. So this is a separation that is kind of commensurate with what we expect with JPass, for instance. So that's what we want to do, basically. We want to get all our galaxies and separate them, perhaps not in 7 different populations, but at least 2, 3, 4.
But this is from simulations.
This is lessons learned from Illustris simulation here. Yeah. But that's what we want to do in real life. Anyway, so now coming back to the issue at hand. So we need to map the universe in all these traces in all these different ways. And often we are attracted to using Fourier analysis to do this, but the universe is not in a box, really. It's not like we can have pictures of the time equals constant hypersurfaces in the universe. So we're kind of forcing a black block into a square block into a spherical hole. What we really want to do is that we want to look the universe. We just want to describe the universe with in the way that we actually observe it, which is in our past light cone. And of course, we can use shells here. And this is already done to some extent, but it's often in the context of imaging surveys or photometric redshifts, where these redshift intervals of these beams are very wide, which means also that you are losing a lot of the radio information inside. So you want to be able to do this for much more fine description of the universe. So you want to be able to do this in very small redshift beams. And there are some technical difficulties of that. This is an issue that was discussed, has been since the beginning of time for large-scale structure, basically. So you want to describe your past light cone here, and you want to have these slices here, and and this is the data that you have here. These are the intersection of your past light cone with some time equals constant hypersurfaces. And there's a lot of literature about that. Of course, the best way to do this is by looking at spherical decomposition and angular power spectrum and so on. This is, I think, is the only right way of doing this. Of course, there's some technical difficulties that I think will be overcome with time. I'll show you some results that are interesting in that respect. But first, what are the difficulties here? Well, the difficulties here is that if you want to have small redshift bins, thin redshift bins, then you're looking at literally hundreds or even thousands of redshift bins between us and, let's say, redshift 1, 2, 3, or whatever. And this means that the number of degrees of freedom that you have is increasing dramatically. So you have, let's say that your survey is limited to some L max because of whatever reasons, either because you don't have the angular resolution, or because you don't want to go to nonlinear scales, but it scales like this. So the number of degrees of freedom just scales very fast. And this is what a covariance matrix of those degrees of freedom look like. If you have, for instance, for L is equal to 10 alone, this is the kind of matrix that you have there, which is that structure there. So it's if you think about this, it's kind of a daunting problem to combine all these degrees of freedom. And we certainly end up needing something like an analytical or semi-analytical approach for this. Doing this numerically is something which I'm not sure can be done. So one way of doing this is that we can do this in the Gaussian approximation. So it turns out that you can do this. You can write the inverse of the covariance for this angular power spectra here, which is also called the Fisher matrix information. You can do this exactly even with redshift space distortions. So this is the general expression here for this inverse of the covariance. These are the noisy angular power spectra here. This is what comes in here. So that's basically for everybody that has done this before. This is just the same statement of the 4-point function. So the covariance of the 2-point function is this. Now, it turns out that you can compute this. So you can either, let's say, you can take the approach where this is computed using simulations, and then you plug this in here, and then you compute that. Then you put this in a chi-square, for instance, a likelihood. Or you can also invert this semi-analytically, and you can do this in this way. This is an approximate formula, which is it's exact in terms of in powers of some of corrections here. But this is an exact expression here with no flat sky, no distant observer, including redshift space distortion. So you can either use simulations or you can use these analytical approximations. It's doable in principle. So you can plug this in there, or you can use simulations to get your power spectrum and then plug it in there. but it's the only way that I know so far is how to use the Gaussian approximation for this. Maybe there's a way to correct upon that, but that's as far as we can go right now. These expressions here, by the way, they look a bit daunting, but these are all analytical kernels which are really polynomials. So this integral you can compute in a matter of a millisecond. These integrals here you can compute in a matter of 1 or 2 seconds, maybe even faster. So this is doable even within a Monte Carlo type approach. Now, so bottom line is we know how to compute a chi-square if you are in the Gaussian approximation. Okay, now, how can I use this now? It turns out that when we did this, I had no idea that I was ever going to use this for this problem, but it turns out that it does. So like Ricardo already told you, we can estimate the distances to gravitational wave events, to binary black hole mergers and neutron star mergers by using the two polarizations, and you can make the degeneracies and so on. So we can know the distances with some uncertainty to these binary black hole events. How can we then use this distance to infer something about cosmology? Because we need to connect that to redshift somehow, because it's not only the distance, we also need the redshift for the velocities, for time, so on. So one obvious way is to use bright siren, which is something that you not only observe in the gravitational wave, but also in optical or some electromagnetic signal that allows you to get the redshift. So this is already, Ricardo showed you this, so I won't repeat myself here, but basically, this is a very simple exercise to show how determining that distance to that redshift of the host galaxy, how that can allow you to infer the value of H0, for instance, right? You can actually do a little bit better than this by using VLBI to settle the inclination angle of these bright sirens, but it's not clear that you can do this in every case. So these are the limits that you can get. This is Planck here. This is the set rates and supernova limits here. And this is what you would get for just that one bright siren. Now, you can also use the line of sight method, which Ricardo was telling you about here. So basically, you have to use some sort of a flyer for the merger rates and the mass function of these black hole mergers. And then you have to marginalize against that, and then you end up getting something which is combine everything that you have, bright sirens, you get the dark sirens with this line of sight method, you get something like this, which is a line that you're seeing there, right? So this is the what the situation is right now. I'll show you a more updated figure here, actually from Clesio, with will be here or maybe not coming here. He's coming. Okay. So this is the, let's say, most popular way of extracting information from dark sirens, so without electromagnetic counterparts. But it depends on priors about the mass distribution, merger rates, and completeness also. It's particularly affected by the poorly localized gravitational wave events. Then your search area becomes very large. And this is the same picture that Ricardo showed you. So I'm gonna skip that. This is just the horizon for observations in the future. Now, this is where some new idea about using dark sirens come in. So think about this. We observe galaxies through their angular positions and redshifts. So we know the redshift. So this is our radial coordinate here, and we have plenty of galaxies. They are perfectly well localized in the sky. Redshifts, if they are spectroscopic, they are also perfect. Now we have been observing gravity waves from mergers for many, many years. In almost all cases, basically no, but basically one or two, we don't know the redshift for those sources, but we do know with some uncertainty the luminosity distance. So we have these two disjoint maps of the universe here, and what we want, of course, is that we want to join them. Why is this particularly interesting here? The distances from black hole mergers is that it's the cliche, which I'm going to repeat. I'm sorry, but The binary black hole mergers are kind of the hydrogen atom of gravity. If you know the properties of the binary, you can know the distance to that, and you have the observation. You can know the distance in principle exactly. We were discussing there during coffee how people are going now to 3.5, 4.5, 5 orders in the post-Newtonian and other approximation, which are like 5 loops. I don't think anybody ever computed 5 loops for hydrogen atom, have they? I don't think so. Yeah, 5 loops now?
Yeah.
I thought it was 4 until some time ago.
There are 2 different groups that have
Right.
loops, and I think they disagree still.
No, but he's asking in particle physics.
Yeah, if you go to the QED vertex.
Right. Okay, so I stand corrected. 5 loops.
Yeah.
Getting that. So basically, it can be known exactly. It's not known exactly because we don't have those properties exactly. We have them through observations, and there are some you don't have an infinite bandwidth to observe those events with infinite accuracy. Otherwise, these would be exact. But there is no systematic in there. That's the point. So these things live in different spaces. What we want, of course, is we want to combine them in some way and extract information from that. Well, that's easier. Well, let me just say that this idea has been along for a long time, so it's nothing new up to here. The issue is how you do it. And this is where I think we come in here. So basically, this picture here gives you a very rough idea. If you join these things together, but you have the wrong model, like here or there, these things don't match very well, whereas they should. Because, of course, I mean, unless something really strange is happening to the universe, these black holes, they are inside galaxies, right? So they have to be in the same places as galaxies, and galaxies are correlated. Now, let me just draw a very simple figure here. So this is the correlation function as a function of radius. And all that I care is that this function is like this. I don't care exactly if it is like this, if it's like that, but it's peaked. And if you find something, to get a galaxy here, it's very likely to have a galaxy around there. So if you have the wrong model, these things won't match. And if you have the right model, they will. But how do you measure that? Well, this is then what we cooked up here a few months ago. Basically, have these 2 maps of the universe. You cross-correlate them in all possible redshifts and distances. So now this is the correlation of galaxies and black holes. So galaxies in redshift, black holes in distance. So these are basically 100 bins in redshift here, and 50 bins in distance here, which are completely uncorrelated. I mean, you can make the bins in whatever way that you want. And this is the autocorrelation of galaxies with different redshifts. This is for L is equal to 100. This is for the black holes here. Very, very weak signal because it's totally dominated by short noise. And this that you see here is the cross correlation of galaxies with the black holes. Now, oops, not this one, this one. We don't really care about this because this is being done already by BAOs and other probes. So this is like, there's nothing new in here. There's little information in the auto correlation of the black holes with themselves, but for the galaxy black hole cross correlation, what you see here, the peak of that correlation is dl of z, pure and simple. Just that peak that corresponds to having highest probability that this z of a galaxy will correspond to a d of some black holes nearby. That's it.
Is the statement that there's not much information in the BBH auto because the signal is very low or because the noise is very high? So then this will also be the covariance for this DL of Z and
no, yeah, right. That's a very good question. So there's no information that you can extract from the signal of that guy, but of course, those 2 everything contribute to the covariance of the whole thing.
Exactly.
Of course, yeah.
So, but if it's, okay. Because if you have like an infinite noise BBH sector, the signal for the cross correlation would be very clean, but you would never measure it as critical.
Well, if you have infinite noise in here, I'm not sure you'll see anything in there either.
There would be very large scatter rate, but on average, it should be correct.
Yeah, right.
Okay.
So, of course, the highest signal will be in here, for sure, right? But in here, you will only see the information about DL of Z clean by doing something like the AOs. Yeah. Right? You don't want to fit the shape. So look at this figure here. This curve, there's a curve here that goes this way here. This is basically tracing the shape of your power spectrum. You don't want to extract information for the LOC or cosmology just from the shape like that. You want to get some scale which is in the spectrum, like the. In this case, I don't care about what's inside the amplitude of that, but only the fact that the peak is over here. That's all that I care. It's always going to be there.
And sorry, one more question. In this, this thickness in Z, this is kind of related to, like in the auto for the, in the lowest, well, I guess this band in ZZ prime for the Galaxy Auto, if these were infinitely thin shells, in the Limber approximation, it should be perfectly diagonal.
No, you always have correlation between different shells.
But in Limber,
In Limber,
yeah.
well, in Limber, I'm not sure, but
I think in Limber it's exactly 0. So I was wondering.
But
if
it
your
cannot be
settings are
0,
correct.
right? There's no 0. Of course, you have correlation between different shells.
No, but if you have one shell in Z and then one shell in Z prime, and there's no overlap between them, in Limber, the.
still a range of AOC,
Like you.
Okay,
But in Limber,
you
there's
don't
no
understand.
line of sight information.
So we are not using Limber at all
Okay,
here.
that's what I was gonna ask.
And for sure, there are correlations between different redshift slices. If Limber misses them, I don't know.
It does.
Perhaps could be, but they are, for sure they are there.
I think there's some kind of magnification.
I'll talk about this. Yes, absolutely. So, yeah,
No, the autocorrelation of BDH is much smaller because it's way smaller the number of BDH you see with respect to galaxies.
yeah, it's dominated by shock. But you see the thickness here in this case here is dominated not really by the shape of the power spectrum or the correlation between different shells, but by the uncertainty in the distances of the black holes. That's what dominates this the spread over in this curve. Okay. But anyway, that's basically it. So amazingly, nobody has done this simple exercise before. And when we cooked it up, we looked around and we found many ideas about how to use this in different ways, but not this simple exercise. So this is basically the method that we are proposing. We have called it peak sirens. That's Miguel's fault for coming up with that name. So basically here is again that figure, that's just a cross, okay? I'm going to completely ignore the autocorrelation information because first, I don't trust it. Second, it's not here. So we are only taking into account that information here. So this is the signal from for L is equal to 100 and see there's every L they have this signal, but it's of course an average of many simulations. So the signal is never as clean as this for a single realization of a single simulation, but this gives you an idea. So this is your true model here, our fiducial model. And if you change the model, this is how it changes here by changing, by about 5-10% the value of each time. So anyway, so let me just say, so this is work that came out just 2 weeks ago, 1 week ago, last week. When was it?
Recently.
Last week.
So this is Jean Perry.
No, last week we were here. It was not last week.
No,
Yeah, I mean, on the archive, yes, because it has been circulating outside the archive, but in the archive. So.
Jean Perry is a PhD student with me. He's in Japan right now. Ian is also a PhD student with me. Isabella is in Portsmouth now. She's a postdoc and looking for a job. And Miguel is here, that guy there. Yeah, I think it's that guy. Miguel is also very. But anyway, you can see here that that's it. I mean, I could stop there and tell you that everything else is just technical details, but I have to convince you that this is robust because, this is, the idea is that this is a cosmic standard ruler. And I'll tell you how.
Into the details. Bright sirens are?
What?
Bright sirens,
Bright sirens are like kilonova, neutron star mergers. You can see an optical counterpart.
but now you're.
This is dark sirens. Black hole, black hole. Okay,
Are you meaning L as well, or L is just?
I'll come to this in a second. I don't know who raised the hands first.
For the error in the velocity distance, do you have like a maximum? Yeah.
I'll come to this also. We simulated this with the best available code for sampling the black holes positions and distances from the known instrument configurations and geographic locations, which is basically something that was done by Jose.
And if you have large errors, you can still do it.
Yeah, well, I'll show you. Yeah. If you have enough of them, of course, right?
Probably for some other slides for this later, but like for how many events is this plot and how can it, like how in this case with the number of data of black holes to have, how it compared with other ways to constrain the distance to the simulation?
Yes, I see.
If it's if you're gonna go to let me know, but how sensitive is this method to how you're actually populating the gravitational waves events into the large scale structure?
Yeah, right. So, can I answer in a few slides? Also, I'll talk about all of this, and if I don't, please let me know, because I'll go through all of this here. So just to remind you, we have galaxies in redshift shells, and then we have dark sirens, black hole mergers in distant shells.
So 200, right?
So 100 shells in
100.
redshifts, 50 shells in this, and that's what we use, but we might have used anything else. I mean, it doesn't really matter, because at some point you don't need to get much more fine than that because of the errors in the distances of the black holes, of the black hole mergers.
So I'm just saying, because at SST it would be, 10, something like.
This is spectroscopic, assuming spectroscopic for now.
Oh, okay.
Yeah, but the redshift bins are 0.02, which is commensurate with the photo-Z errors that you can get from LSST. So what we use there is something where. So just to be sure, we possibly were, but we were not the very first to think about something like this before. There was a paper by Oguri in 2016, and also another one by Mukherjee and Van Delt. But Oguri was basically looking at the lensing signal, which we also compute here. But he never drew a picture like this. He wasn't. He was looking at something similar, but not this kind of observable. And Mukherjee and Van Delt, they were looking at how to extract information from this, from the amplitude of the cross correlation here. So you just take the let's say diagonal here. You just look at that amplitude. It's basically what they were trying to do. So they were not cross correlating different redshifts and different distances and so on. So that's it. Now let's go now to more details here. So what I'll show you now is that if we do this for distances and the redshifts of the galaxies and the black holes, I'll show you that peak, that the fact that there's a peak here doesn't depend on the shape of the power spectrum. It depends very weakly, or the bias of the galaxy or the bias of the black hole merger hosts. Laser magnification makes a small, detectable, but a small contribution. And we don't really care if the black hole is or is not in a galaxy which is in our sample. In fact, we took the most conservative approach possible, and every time that we sampled a black hole we took away that galaxy from our catalog. So 0 black holes have actual galaxies in our galaxy catalog. So there's no coincidence like per galaxy, which if you think about it, you shouldn't really care. When you're talking about correlation function, you're talking about correlating something with the environment, which is many objects, right?
Then you are removing then you're removing the contribution from a potential short noise.
Sorry?
If you by hand remove the possibility that the black holes come from the same galaxies that you observe, you're removing a short noise.
Well, it's cross correlation, right?
But if they come from the same, yeah, there's cross noise.
Yeah, but I submit to you that including those would only improve the signal, not decrease the signal. It cannot be worse than what we are doing.
No, probably you have more signals, you have more correlation if it's well modeled.
If I include the galaxies where the black holes are, yeah, that's my point, basically, yeah. So we don't really need to do it. It's just because there's a whole discussion about the completeness of the galaxy itself, and we knew that it was going to be irrelevant. We compared actually with and without the galaxies of the black holes in each case, and it didn't make any difference whatsoever. So we just kept without.
In this case, I guess maybe because for the number, the cross of noise is low. It may not be increasing the signal if you can't model it right, because like at the end of the day, this sort of noise is going to be Bosonian, so you probably can't use it for signal very well. But it's probably true.
Yeah, it would be dangerous to include that as a signal, though, right? Because it would depend on the model, and we didn't want to be dependent on the model.
Yeah, it would be the covariance.
Right.
But it's probably too low because you probably have like low numbers.
I don't have a solution for how this brought up scale. So we can, discussion.
So just one question. So if in the cross correlation, one set of ALMs comes from galaxies and the other set from black
Right.
holes. So from the black holes to do the projection and YLM, you have to know where the position is, right?
For the black holes, the positions are coming from LIGO, from Mason telescope.
Well, okay,
The distance.
yeah, but where it's coming from, right?
Yeah, well,
There's an error.
There's an error.
Yeah, sure.
Okay,
Yeah, there's always it's a big error.
it's a big error.
So
So
this
that's
is basically the mean of ALM of the galaxy at redshift Z and the A star of black hole at distance D. This here, right?
The method is sensitive to how well you can pinpoint the positions of the.
Yeah, of course,
Yes.
yeah, if you have superb, incredibly good gravitational wave detectors, this would be much, much better.
Yeah.
So we are working just,
if you know exactly where it comes from, you know the
Right.
galaxy.
well,
If you know.
yeah, well, you know the direction, but you wouldn't know the redshift or I mean, think about this, how well would you have to know the position so that you could point to the exact galaxy? It would have to be something of the order of a few arc seconds, right? I don't think that is possible at all, ever. So in practice, what did we do? We simulated the light cone here using glass. And glass is a lot normal code basically, but it gives you also the lensing convergence, which is something we wanted. And I'll argue with you that it's not really too relevant that we have just a simple mark like glass for the galaxies. But then, okay, so this is the galaxy map. We simulated with that. We have about 30 million galaxies up to redshift 2, which is not a lot if you think about it. So it's kind of a conservative number of galaxies, I think. And then the black holes, they were injected using this GW Navi, which is Jose Alsco's together with who else? Jose, you and Ricardo, right? And then that gives us the positions, errors, distributions for all the black holes here. So what you're seeing here is a map using those injected black holes, which are always appearing, of course, inside a galaxy here. And then just as a side, we take out the galaxy every time that a black hole appears there, but we don't really have to do it. But what you see here are these blobs here are the precision with which we know the positions and the distances, the angular positions and distances of these events here. You see, some of them are well localized and some of them are more fuzzy, just because the signal to noise is slow. We don't know their positions perfectly, right? And we use these, we basically make a realization of these errors there in our maps.
Basically, the distribution of these, I showed in one of the slides.
Yeah.
this morning.
Yeah, that was one of the slides. So anyway, about next question, this is a galaxy catalog that has a bias, which we just put in by hand, which is just 1 plus Z for the galaxies and therefore for the black holes. If it's something else, then if the bias is greater for black holes, say that they appear in more massive galaxies, for instance, then the bias will be higher, the signal will be higher, right? That's the, these are the kind of values that you can imagine, right? Yes.
And maybe you have said that, but I don't understand. If you have for the galaxies the redshift and not the distance, and you say that anytime you find a black hole in a galaxy, you remove the galaxy. How do you know that you are removing the correct galaxy? You don't know.
Oh, because the black hole is, okay, so we have the populations here, which are drawn from a distribution, and then they have to be assigned to a galaxy because we want to put them in the context of the large scale structure, right? So you have to find randomly a galaxy where that black hole fits. When we do that, and we say, okay, go to that galaxy there, that galaxy, then we take out from the galaxy catalog.
But you know the cosmology.
No, but I think it's just in the simulation, you know everything.
You know everything about.
Right, in a real case, it could be that the error puts you again in a different galaxy. You think, no, they could overlap because of the error.
Sorry, in the simulation, you do know the cosmology, so you know you can identify them. But in thinking of data, that you don't know the cosmology.
Yeah, you will have some blob like this on one hand, and you have a galaxy catalog on the other hand. All that
You're
you,
assuming a cosmology to identify. a
no,
distance.
no. You measure this directly. There's no cosmology measuring the distances of black holes.
Yes. I
There's no
understand.
cosmology measuring the redshift of the galaxies.
How do you remove the galaxy?
You don't have to remove that in real data. You don't have to.
I don't have to remove
In
it.
the real data, they'll be there sometimes, they'll be not there sometimes. There's no control.
I'm already regretting that we did this because it's totally unnecessary. It's just a step to make sure that we are
Okay.
not sensitive. So it's a completely irrelevant thing, really. Having or not having the galaxies in there is really, doesn't really matter. And we, of course, wouldn't remove them in real life. But we would know which one they are. And why wouldn't we do it anyway, right?
It's just an example to see what happens. You don't have a complete galaxy, but as long as they follow the matter, it doesn't.
Yeah, that's the point.
Since the galaxies are embedded in some bulk hubble flow, do you expect like luminosity distance space distortion?
That's a very good question. So, yeah, what we've done here is for, without redshift space distortions. However, we use redshift bins and distance bins, which are very large. So redshift bins are 0.02 and distance bins are the equivalent of like 0.1 or something like this, right? No, 0.05. Right? So, no, in distance, they are, let's see, what distance are the distance?
Written there.
Like it's either 50 or 100.
It's 50 for distances.
50 megaparsecs.
No, it's just divide 15,000 by 50, right? So it's 300 each.
Yeah. There you go. There you go. I didn't recall.
30 megaparsecs.
So it's large enough that I'm not
300.
sure. So I'm not sure that the redshift space distortion are going to really play a role, but that's on our to-do list to include redshift space distortion.
Luminosity space distortions,
Right.
get to the black holes and redshift space distortion is again.
Right,
Yeah,
right. There is both in principle.
Yeah,
Right?
exactly.
Yeah.
But the luminosity errors are so large that it's probably suppressed. It's the redshift one that would be,
So
because they have
by
20% error in distance, they have a small,
Oh, I thought that error in distance was better. Okay.
no, it's around 10,
Because you expect
20%.
these bulk flow shifts in position to be like, say like 6-ish megaparsecs, right? It's like what the velocity dispersion on CDM gives you, when you convert it to the right units. So if your bins are thinner than that, then maybe you would run into these.
Yeah, but again, each one has an error of 20%.
Okay, then, so-
I don't think it's observable.
Yeah, but it's on our to-do list.
I may have missed this, but like which error for the space localization were you shooting?
Which error?
Yes.
Oh, it depends very much on which, if it's LVK, it's LVK or plus ET, if it is ET plus Cosmic Explorer. So it depends on the network, right? And then you have to use a dedicated code to simulate how that appears in the sky. Also, there's an issue of geography, which I'll come back to, because, you know, when you have the different depths and different places in the sky, you're not really sensitive to all areas in exactly the same way. Also, you have the galaxy in front of you, so you have to cut that out from the galaxy. Therefore, you also cut out from the thrust.
So all that gets into the window, I guess.
Yes, all that gets into
But in the plot I showed this morning, I mean, there spans several order of magnitude, the sky localization of different events, but the bulk is at tens to hundreds of square degrees, the bulk of the.
But it was all simulated anyway. It's all simulated.
Yeah, it's
It's,
also,
make any model.
yeah, simulated with the realistic sensitivity curves of the detector. So-
Of course, if they change in the future, we can redo the simulation.
It has for me to also understand how
Yeah.
much like in or not
So-
equivalent of the beam, because I think
Right.
it means not
So you
necessarily.
can see that some of these are like skewers here, right? So these are errors which are like 20% in this.
Yeah, no, like I was also curious for like how, like what range in L did you have?
What in range and what?
Range in L, because
In
the
L.
localization is going to.
That's a very good question. I have an extra slide for that. But basically, for LVK, it's basically up to L of about 150. If you use LVK with the Einstein telescope, then the maximum L that is really doing anything is about 300. More than that, you just
Oh, yeah, I don't know.
erase there, right?
So just for me to understand, use the first catalog of galaxies
Yeah,
generated by
we start with
Flash,
that.
and then you produce the second.
Yes. Yeah. So we did this.
Some probability of a galaxy in this left catalog to host
Yeah.
a
Yes.
black hole.
Exactly.
And this probability is from a PDF or something.
Yeah, that's it.
Yeah, but I mean, one doesn't really need the galaxy catalog for the blind black hole. If you you would just generate binary black hole with the same statistical properties. So it's much easier just to pick the galaxies instead, provided you generate something with the same statistical property.
But you have to put the black holes, of course, in a galaxy in the context of the large scale structure, otherwise you miss the large scale structure correlation, right?
What is the PDF that you use?
The PDF, oh, I don't even know how to, it's a whole code that does that, right?
You know the N of Z, and then you select randomly, just using N of Z, nothing else, because it's for class.
So have I missed any questions that people asked before? Because I said it's like later.
Is class, which is what one multiplies those?
Is the next generation of class 3.0, 4.0, whatever.
So then there's.
Sorry?
No, okay.
Yeah.
You can speak.
So we did this literally tens of thousands of times, and we needed to be fast. So that's the main advantage here. It creates a light cone. It has lensing. So it's what we needed. So this is maybe this answers your question. So this is the PDF if you want. These are the errors in the angular position and in distance as a function of redshift for the three networks. So LVK 05, so that's the next LVK, which is going to start in a couple of years. Then this is LVK plus Einstein telescope, and Einstein telescope plus 2 cosmic explorers. You can see that, LVK together with Einstein telescope already done a superb job in determining better the angular positions and distances here that you can see from these plots there, just because of the triangulation that Carl was describing before. And of course, Einstein telescope plus cosmic explorer does even better. So this is your sensitivity across the sky for LVK. But then if you average that out over years, let's say, you get something which is more homogeneous. And of course, your galaxy map doesn't care about that. It's always there. But if you have a joint BBH PDF, then you get something like this. So of course, and this line here is what we use to cut out the Milky Way, super simple cut. And that's another thing we have to do it better. What would it look like if you have a more complicated mass in there? It's also something we want to see. So we have about 30 million galaxies at redshift 2, sorry. And we use a Milky Way mass, which is a latitude of 20 degrees up and down. I don't recall exactly, 20 or 29. 20, I think 20 degrees in latitude from the galaxy.
So that's the error of the log of the luminosity distance as a function. Right?
Yeah, that's in logs.
Fractional error, 10%, 5%.
Oh, that's 10%. Okay.
Yeah, the log is a very fraction.
So
So you see that for LVK, the vast majority of events, except for a few, they have errors which are bigger than 10% in, well, this is log of 10, but anyway, so these are high errors here, and these are the one errors for in degrees, square degrees, yeah.
So for you to have like signal, how many black hole and dark sirens do you need? How many events?
Oh, well,
Order of magnitude.
well, I'll show you the constraints, and then I'll stop. And you can see how it goes from LVK to larger networks to O3 to third generation detectors, and then you can estimate how that goes. But it's basically with the number of events, and also, of course, it depends on the signal to noise too. So it's not only a matter of the number of events, but typically, if you have many more events, you will have higher signal to noise events coming together, right? So, but I don't have an answer for how exactly a certain figure of merit scales with the number of events and how that's going to grow over the years as we integrate more and more events. I don't have that. So lensing, yeah, somebody asked, right? So this is without lensing and with lensing, and you can see that there's a slight difference by eye, you can see that. So this is the prediction was done by Oguri in 2016 in that paper that I mentioned before. This is what we actually calculated from the simulations. And so this is the yellow lens here in yellow. And the contribution from lensing is this dashed line here. So you have a bit more magnification and a bit less demagnification here. So the effect of lensing is that it gives you a bump over here, of course, to lower redshift than your black. So this is basically fixing the black hole events at a redshift of 1. and then you ask what is the cross of the galaxies with that black hole event. So because of lensing, you get a bit extra buck here to lower redshifts, of course, than the event that you're measuring, but you also get a bit demagnification here. So what the effect here is that it shifts this peak very, very little, just a little bit, but it's detectable in principle, and I'll show you a figure that shows you exactly how much.
Did you consider cosmic magnification, sorry, in the galaxies?
Well, this is the
Because that's like for
this
the
is the
gravitational wave.
this is the lensing of the galaxy center.
No, that's like for the distribution of the binary black holes, right? Like from what they see in the region. I mean like cosmic magnification in the cross correlation with the rest between the galaxies.
Right. So I think this is a mistake here. I think these are the lensing of the galaxy.
Because wait. Lensing changes a bit the distance here.
Oh yeah, no, sorry, yeah.
For the black holes.
That's
You
it.
only have the red.
Sorry,
The
yeah.
laser does not change the red.
No, like, not going to use
Yeah.
accounts. It
Sorry.
produces correlations in very separated.
No, I
Right.
think what you're saying. So.
No. It's the lensing, if it's magnified, it decreases the distance just a little bit.
No, I understand that for the
Right.
gravitational waves, but it introduces correlations between your galaxy correlations at separated recipients
You change a bit the power spectrum, that's what you're saying, right?
and introduces covariance.
Yeah, that's
Right.
That we don't.
So we haven't included the lensing of the galaxies in the sense of increasing the counts of galaxies,
Yeah.
because the recipe doesn't change.
Yeah, no, it's just like capturing the correlations,
Right.
like the
So-
correlation that you see like
Right.
between the two.
So it took me a while to spin my head back. So the only difference then would be the increased counts of galaxies, not the redshifts. And for the black holes, however, you do see a different estimation of the distance to that. So that's the effect here. We happen to include lensing of galaxies that affect the maps of galaxies in any way. That would be something else, right? But you guys can see that because of magnification, you just make them a bit, just a bit closer, and you can actually detect them when you're measuring, when you're using this cosmic standard ruler. Okay, so what are the forecasts? So this is for LBK05, so the run 5 of LBK. So that's going to be happening in a few years from now. We are basically including the standard numbers here, which are about 300, 350 events, up to redshift of about 1. And these are the constraints that we get, joint constraints between omega matter and H0. And here is just constraint of H0. If you fix omega matter to the fiducial value, just as a comparison, so this is basically about a 5% error in H0 that you can get just from that test. As a comparison, just as a comparison, so this is about 4% precision. This is the situation right now. So this is a fair comparison. Of course, this is for what we have from combining all of the bright sirens and dark sirens in the line of sight method. This is a paper by Clesio. Maybe you will be talking about this tomorrow. So this situation right now. So this is the data that we have right now. Of course, these figures will get better by the time LBK makes it run there. But it's basically 6% precision right now. So it's comparable with LBK there.
It's also using the bright side.
Which is also using the bright sirens,
That's not-
yes. By the way, yeah. And this is fitting for H0 alone.
The bright side.
So bright sirens is this one here.
Yeah.
Combining bright and dark sirens. Dark sirens is this one. That's the line of sight method. This one here. So the fair comparison will be with this blue line here, with this dashed line here. Be the fair comparison, but again, not fair because one is the real data that we have right now, the other is future data that we'll have in about 6 years. Okay. Now, in the future, that's maybe 10 years, Einstein telescope, something like this. These are the constraints that you will get from omega matter and H0 here. So we're talking about H0 error of about 1. So we're talking about percent lab accuracy in H0. So that's assuming about 50,000 events at redshift of 2. Again, our best estimates for what Einstein telescope will observe. And again, LBK, the history of this project was like this. We thought initially that, oh, we're surely going to need like Einstein telescope, 2 cosmic explorers, and maybe more. So we get this first. I said, it's pretty good. So we start with this. And it's, oh, it's good. So we try that. Well, it's very good still. And then we come to this. It's like, well, still very good, to our surprise, because these are only about 300 events, which are not very well localized at all. So, that's the story of this effort. We were scaling back and saying, no, I'm really surprised. But anyway, so that's the situation there. Now, what I think is the most interesting aspect, yes, Nick. No, go ahead.
Galaxy sample that is being cross-correlated here, I missed this. Like, what's the assumption? Is this like analysis T-like sample that you're cross-correlating LVK with?
No, I don't have any galaxy map in particular. I'm using a bias. It's a simulation with a bias of 1 plus D.
For the covariance,
30 million galaxies.
30 million galaxies. Now to redshift 2.
That in redshift, or what is the DNDC that to consider?
Oh, it's what's the name of the fitting function that we use? That funny name. Anyway, what's the name of that?
It's a generic prediction.
Yeah.
It should be, because this is 10 years from now. So this is after, DESI 2.
I'm sure that the galaxy sample is way underrated.
Yeah.
30 million galaxies, and almost I mean, forget it.
I think it said like 3 billion or whatever. Like,
No, 3 million. Sorry, 30 million to redshift 2 in 70% of the sky. I think that's very, very, super, probably ridiculously conservative, but that's what we started with, and then we ended up. The thing is that it doesn't really scale. Once you reach a certain threshold in galaxy number, it doesn't really help you to have 300 million or 3 billion, because you basically map down the regions where the black holes can be. So it doesn't really, you don't really care. I would much rather go for control systematics of that map than having more galaxies that I don't understand very well.
Probably you can even engineer some DNDC to control the sample to improve
I could,
the coverage.
we could, I guess.
So for the graph on the left, how many galaxies, and so it's for 300 events. The galaxy survey.
So I don't recall the number of galaxies in this case here, but it's, we have more than that for sure. But maybe not for, the issue is having galaxies in here well distributed. So this is the challenge is getting a larger area, but I think we're getting close to this anyway, because of all of these, Desi Legacy and unions and all of these surveys joined together. They will give you pretty large analysis T, of course, right? Anyway, so this is what we have for W0, W8 lambda. No, there's no lambda here, of course. Forget. W0, W8 CDM. This will be a funny model indeed. So this is what you get there. Of course, the constraints get a bit larger, but this would be, again, a completely independent test of, this is cosmography. You can do whatever you want in cosmography, right? You cook up whatever you want. Now, what I think is most interesting here are the robustness of this. And so let's make some stress tests here. So yes.
This last thought, is this I think I saw something about it being Dali-like. It's not an MCMC, it's just a 4th order Fisher.
No, that's
It's for MCMC.
I'm not sure how Raul smoothed out things, but it's an MCMC.
No, I'm mostly interested in, because like for a lot of these cosmography things, people have pointed out that if you have like omega matter misestimations and things like that, then your W0, WA will shift in some like down into the right. And so I was curious if this would also be sensitive to that, but
I don't know.
Yeah.
you're looking at not H not and dot those W.
You're looking at this.
No, the bottom right panel, like, yeah, so,
That's the right word.
yeah.
Yeah, you can see this correlation between W0, WA and omega M. So yes, this missing one,
Well,
gonna miss the other.
This cannot be too different than doing cosmography with some other probe, right? It just, the difference here is that we don't have any calibration. So, that's something I'll say. I've had that written at some point, but, I just took it out because, it's one of those things. I cannot see as of now any super obvious systematic that would spoil this picture. But of course, I didn't write that down. You just heard it from me. So the knife is like that bad. I never said that. But here are the tests that we made. So this is the test where we use large scale structure from one simulation and the distance from another. We're just saying, are we recovering the right distance, even if we use large scale structure from a completely different cosmology? And we do. So we use basically fiducial cosmology here for large scale structure, but distances from one cosmology, we cover one cosmology.
Have you done tests of like how suboptimal you get?
How what?
Suboptimal, because I guess that like the optimal errors would be if you assume the perfect model. This is just curiosity. Model what?
You mean directly comparing the chi-square between that fit here and that one?
Yes, or the posterior in omega 1 and it's not.
They are basically distinguishable I'll show you another picture that goes along that line, but no, we haven't compared. I think the chi-square is very
get not suboptimal, that's very
right.
I didn't understand what's.
so like I understand why it's robust and you have no bias, because at the end you only care of like when you have the maximum overlap, because that's when it's going to maximize your correlation. But I would expect it to be slightly suboptimal if you don't have the perfect power spectrum that you expect in your model.
Right. So I'll show you another one, which is another stress test that we've done.
Discussion. So the fact that you see that the shift there by I is less than 0.2 sigma, I don't know how we can get more than whatever we shifted there by using a more optimal EFK. I understand what you're saying 1% about the precision, but if you made a big difference, you would have seen a small bias there. Don't know how we can not see a bias and still maybe MDC.
No, but the one here is the bias that you get, and the other one is the size of your errors.
I know, but
yeah,
the fact that you're blind to the thing, it has no bias, and you still think that.
That's a good question. We haven't.
I mean, this was curiosity.
Yeah.
Because when these kind of things are like robust but suboptimal, or unbiased but suboptimal, that is like.
Right. No, anyway, I'll show you another one that maybe goes along this direction here. So the second test we did was lensing. And let's say that can you guys see this very light line here? You get close, right? So that's when we turn off lensing entirely. So no lensing. As opposed to lensing. If you turn off lensing, then you get a little bias here.
You choose the best background for this bias.
So you can see this here. So this is shifted to the side here by, a fraction of a sigma, but it's detectable. But, I don't think this is a completely radical example where you completely turn off lensing. It's not a matter of having a better or worse modeling of lensing. It's just completely turning it off, which we know is a crazy approximation, but the bias is still very small. So, we typically, when people have looked at this, different lensing, different modeling of lensing, the difference is very small. So I don't think this is going to turn out to be super relevant systematic. And again, this is for Einstein telescope plus 2 cosmic explorers. So this is a super futuristic, that when you're having super high precision there. But this is the most interesting one here, I think. So this is when we use in our data the glass with a halo fit power spectrum. And if we turn off halo fit, so no nonlinear corrections there in our power spectrum. And the difference is, you can perhaps see here a tiny difference there. So again, no nonlinear corrections in the power spectrum that goes into this. So
that's
the question
L
is,
equals to 100.
sorry?
That is for L equals 100.
Up to 300 L there. It's not saying it there.
Okay,
But
300.
we effectively go up to L of about 300. So what this is saying is that, it doesn't really matter if the correlation functions are like this or like that. This is kind of second order, because what you care about is the peak of the correlation function. So, this is, I think, the most interesting aspect here. I don't think that nonlinear effects will be a relevant systematic or super important systematics. We, of course, are working on making better simulations where we can do this test even more stringently by having a more realistic nonlinear modeling and turning it off and seeing what happens, right?
So 300 is the maximum that you went with L.
Yeah, I'll show you I'll show you a picture maybe later for the.
I just wonder if you get something better.
Let's
if you go-
converge. Let's converge on that.
Asking for-
There you go. Here is the figure of merit for LDK. Basically, when 750, 200, it has basically saturated. For LBK plus ET, it saturates at about 200 and something. For ET plus 2C, 250, 300, that saturates. So anything else, you're just washing out the information, right? Okay, that answers that. Yeah, about this?
Oh, about the like systematics. Yes, is there anything on the side of the like gravitational wave detector? Like, is there a point where you need to care about how like volts screening? Is there ever the possibility of some systematics from the gravitational wave detector side?
That's a question for the discussion perhaps, or for you? I have.
There isn't, I mean, there is no.
How would all volts be constraining to do you need to care about that as well?
If you're not in GR, then would be wrong in the distance.
Yeah, but I mean, then we have been quite generous for the error in distance. So, I mean, unless there is really a bias pointing always the same direction, we have investigated that is implemented bias in distance and sky position.
Let's say you have a different gravity theory.
Yeah, if not in GR, it could be biasing everything a bit.
Yeah, but that's really bias always in the same direction.
That's what the bias is.
Anyway, so I think the conclusions are obvious here, but anyway, just to recap, this is a very robust method. It just relies on the fact that that galaxies are highly correlated, and when they are nearby, you have a peak in correlation. So we don't need any electromagnetic counterparts. So this means that the vast majority of black hole detections, they can be used up to very, very high redshifts. And we get about 4% constraint on H0 when you're just constraining that alone with LBK 05, and about 1% constraints in the future with Einstein telescope, even just combining with LBK. So that's the horizon for, I'll be optimistic here, 8 years, maybe 10 years. Right. And to do here is, you guys already exhausted the list of what we need to do. So there's no such thing as schematic free. What is the bias of these black holes versus galaxies? This should affect the amplitudes, but is it going to distort the signal? Our samples of galaxies and other high redshift tracers, they are sensitive to angular redshift selections. So, combining imaging spectroscopy, it might be a bit more delicate. Different configurations and perhaps systematic errors in the distance of the black holes events, and including redshift space distortions are some of the things that we are planning to do. And I think, right now we are working, by the way, this means led by Isabella. We are already working on combining LBK data to run 4 with a galaxy catalog called Glade Plus, which is popular among gravity wave people, because it just covers a very large area. It's not very deep, but it covers a large area. So that's what we are working on to get the constraints from peak sirens for the present data. And before I finish, let me make some shameless propaganda here. We have a position open in the University of São Paulo, a faculty position, a tenure track position. Applications are welcome until the end of the year, beginning of next year. If you're interested, talk to me. And thank you.
As you say, the questions for the discussion. One urgent.
Not over there, can I ask you?
Yeah.
Do you have enough, or do you expect to have enough signal to noise pair bands in multiple so that you can do internal cross checks? I mean, it seems that you don't have systematics, but it will be very cool to see, for example, that of course you're going to have less signal to noise, but results from I don't know, 0 to 50 and 50 to 100 are on top of each other.
Yeah, so in part, this is what this picture shows, but it's cumulative here, right? So this is the constraints for cutting out there. So yeah, I think it's possible to have just the constraint for up to 100, 100, 200, 200, 300, and see if they match, if they are not, if you don't have a blob here, blob there, right? I think, look at this figure here. Look at these types of figures that you have there, at least for Einstein telescope plus 2 cosmic explorers, but even for
I mean, because the cat's there, or
even for this guy here, right?
Let's see.
You can think that this region is going to increase by a factor of root of 3, right? And then you have 3 of them, something like this.
Yeah, I can imagine like those kind of projects or impressive, and impressive, you will see like different galaxies, but they also overlap.
Yeah.
That's really good.
Or for different redshifts also, right? Same thing, you get the whole range of L's, but you split in redshift bins, so you know, 0 and 5. Something that I didn't talk about, we didn't ever consider was that we were not really thinking about traces at very high redshifts, but you know, if there are events on ICE telescope and Cosmic Explorer that go to redshift of 10 or 20, decimatic could be used for that, but it's not clear that it's going to be events in that case. In any case, cosmography, it's really a game that you win at low redshifts more than at high redshifts.
I think
I mean,
gravitational
depends
wave,
on what.
gravitational wave can be above redshift 2. I think that's not the question so much. I mean.
Yeah,
that's the universe is a
But the
bit-
number of events,
but,
right?
Yeah, the number of galaxies, it becomes a little bit more speculative.
Yeah,
right? The
yeah.
30 million was very conservative. Now if you go,
Right.
we're gonna have between 2 and 5.
Yeah, so the models for how we populate the black holes are probably safer and lower redshifts, whereas for higher redshifts, it's more,
Yeah, we just don't know if the sources are there.
right?
Whereas for galaxies, it's even worse because we don't know, actually, we know we cannot observe galaxies. There.
Yeah. So if anybody can think of another systematic test that we should do, please tell us. I mean, we are working our way through many of these. It's a new test, so you know, it's sometimes it's the thing that you're not expecting that's bringing up some caveats, but that's what we are committed to do right now, doing all the tests that we can. So if you can think about something that can be an issue here, please let us know. Because we are starting to do all those tests now.
Redshift 2 to 5 should be fine from the galaxy
Sorry?
side. Redshifts 2 to 5 should be fine from the galaxy side.
For future service.
Yeah.
No, DESI 2, which is starting next year or very imminently soon, we'll do 40. But there, I mean, it's like really on track. We'll do like 40 million galaxies, right?
There's extension and then there's it
Okay.
25 years.
No, I mean, for sure there's stuff that we can use, even quasars, right? So we just want to be very conservative at the first paper, you know.
Yeah.
No, but
It will be,
it's
there'll be,
Dropouts, yeah.
there are quasars as well that can be used, because again, the number density of black holes is the dominant part.
Mhm.
Right? The fact that you have few quasars, usually it's very bad for BAO, but for this method, it's not so
I
bad.
agree, I agree.
Yeah, so this paper is more like a proof of concept with some baseline things, and then as we get more.
I think it's not the
See, and
mistake.
as soon as we have an actual catalog that we say, okay, we can use this,
Mhm.
then you can do something which is more targeted for that catalog. Right now, it's just a very generic survey, which is conservative enough. That's the idea.
Okay, so I suggest, keep your question for the discussion, but let's refresh with coffee and think about.
Thank you. Should I leave my laptop here in the zone?
You can use it for discussion.
Okay.
Now, it's going
Yeah, it's important.
Very, very cool.